So in this problem, we have someone pushing a box up a ramp, and they're pushing it at a constant speed, and the force that's parallel is 25 newtons. So we know if this is the force parallel, this 50 newtons is just the weight of the box. This is the force that's doing the pushing, so this is the force that's doing the work. So the question is, calculate the work done on the box by the student while pushing the box up the incline, from the bottom to the top. So the force that's parallel, that's going to be the 25 newtons, times the 6 meters pushing it up the ramp. So that's 150. But I just wanted to show you that even though they didn't ask this, had we done it the other way and solved for the work doing the potential energy, we would have gotten a different answer. Because the work to lift it vertically, that gives it PEG. That would be mg, the weight of the box, times the 2 meters. Why is this less than this? Well, it's because there must have been heat produced and there must have been friction by 50 joules. The second question says, what would happen to the total work done on the box by the student if everything else is the same, 6 meters, constant speed, if the coefficient of friction between the box and the incline were increased? So if we made the coefficient of friction larger, then the force to pull it up the incline would increase. If the force is increased, force of push is larger, the work would be larger. In this one, we have a spring where they give us the spring constant. They give us the amount of energy. It says elastic potential, so that's spring potential. And it says calculate the spring's change in length, so they're looking for x. So we set up our formula, PES equals 1/2 kx squared. They gave us the energy, they gave us the spring constant, so all we have to do is solve for x. In number 4, they have a motor doing 20 joules of work on a block. So we know the total work done on the block. And it accelerates the block vertically upward. So that means that it's accelerating, so the block is gaining kinetic energy, but it's also gaining height, so it's also gaining gravitational potential energy. So if the total work done is 20 joules, and 15 of that turned into gravitational potential, then that means 5 joules must have been the kinetic energy that it gained due to speeding up from that acceleration. Number 5 says, what is the rate at which work is done? Well, we know rate at which work, rate is with time, so that's the rate at which work is done, that's power, to lift a 35 kilogram object vertically at a constant speed of 5 meters per second. Well, we know that power is work over time, but that it's also force times average velocity. Well, the force to lift an object at a constant velocity is equal to its weight. So we can just put in mg for its weight, 35 times 9.8, multiplied by that constant velocity of 5, gives us 1,715 watts. In this one, they give us the amount of spring potential energy, elastic potential energy, so that's PES. And when it is compressed, 0.2 meters, so that's our x. What is the spring constant of the spring? We're looking for K. So we have PES equals 1/2 kx squared. They gave us the PES. We're looking for K, and they gave us the spring compression. So solve for K, and that comes out to 500 newtons per meter. This is a rather involved problem where they're asking us lots of stuff about this skier being dragged up the hill. So first off, they give us the mass of the skier, 72 kilograms. And they tell us that the height of the hill is 40 meters, but they also tell us that the length of the hill is 230 meters. And here's the important part. It says the tow rope exerts a magnitude of 158 newtons to move the skier up the hill. So that's going to be our force parallel to the plane. So to do that, we're just going to do W is equal to FD, and we're going to use that parallel force, that's force parallel, times the displacement of 230 to get our work done, 36,340 joules. So the next question is, calculate the total amount of gravitational potential energy gained by the skier. Well, The skier is gaining PEG because they are going up a height of 40 meters. So when this happens, we just find the MGH. So that's 72 times 9.8, the weight of the skier, lifted vertically 40 meters. That's their potential energy, 28,224. It says, describe what happens to the internal energy of the skier hill system as the skier is pulled up the hill. Well, internal energy is the heat. So if we look at this answer, it took 36,340 to pull it up, but they only gained 28,224 of potential energy. Where's that missing energy? That's what the Q was produced. So they are producing more and more heat as they go higher and higher up the hill. And finally, in number 10, it says, what happens to the total mechanical energy of the skier hill system? Well, the skier is going up the hill, so work is being done on the skier, so the skier is gaining PEG, and that's a form of mechanical energy.